Hello everyone, my name is Zijun. I come from Shanghai Jiao University, EPCC Lab. Today, I will give a talk to introduce FaaSFlow, enable efficient workflow execution for function as a service. In this section, I will briefly introduce what serverless and FaaS are, and how we usually run a serverless application. First, what is serverless? According to Berkeley's view, serverless equals FaaS plus BaaS. Developers upload their codes as functions to the FaaS system. User triggers a function through events, like HTTP requests. The FaaS system allocates computing resources and interacts with the backend services to execute functions. When functions need to communicate, the serverless application can use fine-grained functions to provide complex functionality by connecting them into workflows. They are usually known as serverless workflow. Take the video transcode workflow from Alibaba use cases as an example. Developers have to define the workflow with 5 functions: upload, simple trans, split, trans, and merge. Besides function codes, application developers also need to additionally predefine the control logic by workflow definition language. Serverless computing has become more popular for many advantages, like offloaded management, auto-scaling, pay-as-you-go costing model, and higher resource utilization. They together make serverless-based deployment more flexible and resource-friendly than traditional IaaS-based deployment. However, it also has limitations, such as relative high latency, inflexible state management, lack of the data locality, volatile storage, and heavy communication overhead. Considering these limitations, does the serverless model make your application run more efficiently? Unfortunately, no. So, in this section, we will analyze the efficiency of the FaaS model and where they come from in serverless computing. On the one hand, function invocations are non-addressable to users, either due to the dynamic serving address with cold startups or load balancing policies as warm startups. As a result, the serverless platform usually introduces a centralized engine or controller to help with the processing. This process introduces additional scheduling overhead. The dispatching of a function invocation usually has 3 steps: task assignment, execution, and state return. We call it the master-side scheduling pattern, or master SP. For example, executing the following workflow requires several TCP connections to complete the state transfer and task assignment. This engine also needs to determine how, when, and where to assign a function task to worker nodes. Because there is currently no distinction between a single function and the workflows in the serverless engine, each function invocation in the workflow needs to experience all 3 stages. The overhead in this process is large. To this end, the first challenge is whether we can reduce the overhead of master-worker task assignments. On the other hand, when reorganizing a stateless application into the serverless workflow, the data shaping pattern brings frequent data movement to the function side invokers. Let alone more data movement is required with fast architecture. Because the data needs to be reloaded when auto-scaling and saved when containers are recycled, application developers must transfer temporary data by remote storage or RPC payload. Although there are some efforts to enhance the data locality by sharing the payload in RPC, it still has many limitations. While the data-driven functions cannot utilize the data locality, the data transfer through the network becomes necessary. However, due to the traffic control in the data center, the bandwidth of network and the size of the RPC payload are also limited. Here comes another challenge: how to transfer large data efficiently between functions. So far, we have analyzed the reasons for the efficient execution of serverless workflows, which are mainly reflected in two aspects: scheduling overhead due to the frequent state transfers and task assignment, and unnecessary data movement due to the lack of the data locality. So, how does FaaSFlow solve these challenges? We have three main optimization points: the graph scheduler, worker side scheduling pattern or worker SP, and adaptive storage called FaaStore. First, FaaSFlow still follows the master worker architecture design. However, the master node is only deployed with a graph scheduler to partition subgraphs for worker nodes. Specifically, we use a heuristic algorithm for faster response. It will find the edge with the highest weight in the critical path of the DAG, then group the adjacent functions into the same subgraph if only restrictions are satisfied. For example, the algorithm will merge the green and the black functions into the same subgraph, and then start the next iteration. Second, each worker node is deployed with a decentralized workflow engine that follows worker SP to trigger and manage functions. Because the DAG is predefined and partitioned by the graph scheduler, functions become addressable in the workflow engine. It makes worker SP possible to provide a faster and more efficient workflow execution logic. For example, 4 functions are divided into 2 subgraphs that managed by their respective workflow engines. When function A gets executed, the execution state turns to be true and is directly transferred to the function's successors without master-side task assignment. It should be noticed that the protocol for cross-node TCP communications is only responsible for updating function states. Function B and C then will update their predecessors that executed and judge whether all parent functions are complete. If so, the function will be triggered and scheduled locally by the workflow engine. Besides the design of worker SP, the addressable feature or functions in the same subgraph also make it possible to localize the temporary data. Users use a unified API called FaaSStore to save and fetch data. FaaSStore will adaptively select local in-memory storage or remote storage according to the subgraphs. The in-memory cache is dynamically reclaimed from the idle containers to provide an adaptive quota for data transmission. With the above designs, FaaSFlow can make serverless workflows run more efficiently. In this section, we will introduce our evaluation process. We evaluate our system using 4 scientific workflows and 4 real-world applications. These workflows are defined by DAG and include 4 basic logic flows: sequence, parent, switch, and for each step. We use an 8-node cluster setup. The workload generates the query following the closed loop when avoiding queuing. The timeout is set at 60 seconds, and using WonderShaper to set a network bandwidth. The results show that FaaSFlow effectively mitigates the workflow scheduling and data transmission overhead. When the network bandwidth changes, FaaSFlow reduces the throughput degradation by 23%, and it also can multiply the utilization of the network bandwidth. Finally, we give our conclusion and discuss the future work on FaaSFlow. In this talk, we detailedly analyze the scheduling and data movement overhead, and how FaaSFlow deals with them. First, by a graph scheduler, a serverless workflow is partitioned into subgraphs. By a new scheduling pattern called worker-side scheduling pattern, or worker SP, a function can be triggered as soon as all the predecessor states are updated, rather than waiting for the task assignment from the master node. Finally, by adaptive storage called FaaSStore, functions can select local in-memory storage or remote database storage to transfer temporary data. We will also explore in the future how to implement the data flow in the worker SP-based architecture, and then reduce the QoS violations when multiple workflows are collocated. You can get our paper and the FaaSFlow on GitHub for more details. You can also contact us by email with any questions. Thanks for listening.